Okay, great. Okay, so I'm not really going to talk about some results that we have. Rather, I'm going to talk about some very early stage idea that I've been exploring with Marco Patrignani, and I think it nicely fits in the Prisk community. In particular, I'm going to touch about some of the topics that Hugo mentioned during the keynote, and in particular, what kind of stuff compilers can bring to the table when we're trying to fix microarchitectural attacks. Okay, so let's start with processors. Processor, everyone knows processor at the core of all our systems. They effectively run stuff. In the end, everything passes through a processor at some point. Recently, however, researchers discovered a gazillion of new attacks in the last few years. Each of these attacks come with a very fancy logo. People can be very creative. And the key idea is that these attacks target processor security. And in particular, they do this by exploiting microarchitectural side effects that result either from processor optimization, such as processor optimizations on how instructions are executed, such as speculative and out-of-order execution, or the side effects introduced by internal buffers and caches that in the end are invisible at the instruction architecture level, and all the side effects are actually exploited to compromise security of applications. So the short summary is kind of processor security is a bit broken. So in this context, what can programmers do? Well, to write secure programs, programmers need to take these side effects into account, and they need to somehow program defensively to avoid potential leaks. And this is already a daunting task. To make this even worse, unfortunately, there is no unique reference for microarchitectural side channels. And the reason for this is that different processors and different generations of the same processor have differences in the internal microarchitectures, and somehow in the end they provide different levels of security. So just to give you a concrete example, even a simple instruction like CL flush, which triggers a cache flush, has, in the end, different microarchitectural side effects on various generations of Intel processors. Okay, so the summary is that we have a ton of side effects, each depending on specific processors and specific internal details of what's going on. And programmers have to take all of these side effects into account when writing programs. And well, this is simply unrealistic. We cannot and we should not expect programmers to manually tailor programs for specific processors and for their security guarantees, I would say insecurity guarantees. And this is where we believe that compilers can help fixing this problem. And in particular, compilers can bridge the security gap between the ISP level and the microarchitectural level with all these side effects without really requiring programmers to think too much about all the side effects. And yeah, and somehow our idea is that compilers should target specific processor security guarantees, and they should leverage these guarantees to produce secure code. Concretely, compilers should generate different target programs depending on the specific CPU that we want to run the program on, and depending on in the end on which attacks these CPUs are vulnerable to. So if we can get this kind of smart programmer that can fix the microarchitectural issues for us, then programmers can simply focus on program level security. For instance, programmers will have to ensure that secrets are not leaked under the source semantics, while compilers will take care of microarchitectural security concerns, like, let's say, preventing leaks due to caches or due to speculative execution. Okay? So this is a very high-level vision. We don't really have too many results in this direction, but we do have a clear view of, or we do have a reasonably clear plan to achieve this. And this is what I'm going to discuss in the few next slides. Okay, so the first thing that we need is, I've been talking about microarchitectural side effects. Well, we need a way of modeling this kind of side effects, and we need a way of expressing the processor's microarchitectural security guarantees. And for this, I'm going to use something that we call Arbor Software Contract, which we recently introduced in an open paper. And the key idea is that contracts are an abstraction for distributing security obligations between hardware and software. And in particular, we focused in this paper on information flow properties. So this is the setting that I'm going to play with in the rest of the talk. So contracts precisely capture hardware-side channel security guarantees in a way that is mechanism independent, so it doesn't rely too much on what's really going on internally inside the hardware. And the framework consists of, let's say, two main components. First, we have a model of a processor. So processors are modeled using a hardware trace semantics, where observations model sequences of microarchitectural state that happen during the execution. So, yeah, for instance, we have these red curly brackets that is the hardware trace semantics. So this would say that, executing the program P on the CPU, starting from an architectural state, initial architectural state sigma, then produces this sequence of potential microarchitectural states. And the second big component of the framework is contracts. So contracts are modeled as labeled semantics for the ISA language. And the key point is that the labels in the contract expose security relevant microarchitectural events during the execution. Let's say, for instance, the address of a memory access or the outcome of control flow statement. Now, given these two components, given these two models, the framework precisely captures the notion of a processor satisfying a contract. So this is actually, let's say, the semantic meaning of contracts. So we can state that a processor satisfies the contract, and we can prove that the processor satisfies the contract. The intuition behind this notion is that whenever a processor satisfies the contract, then initial architectural states that produce the same contract traces then are guaranteed to be indistinguishable according to the hardware trace semantics. Okay, so the short point is contracts provide a concise way of semantically characterizing, let's say, leakage models or and processor guarantees. Okay. So concrete example, what we did in that paper is we defined several contracts for modeling guarantees provided by different hardware level countermeasures for preventing Spectre-style attacks. So we came up with a bunch of contracts which are shown here in the lattice. So each of these contracts capture a slightly different leakage model. And just to give you some examples, for instance, we have, let's say, a bottom contract that corresponds to a CPU that would leak everything, top contract corresponding to CPU that leaks nothing, and a bunch of things in the middle, for instance, sexcd, which is the standard, let's say, constant time observer, where we can see addresses of load stores and instruction fetches, secarch, which is a slightly weaker version that discloses more information, and speccd, which is, let's say, which is very similar to the speculative constant time model considered in the talk, considered in the talk previously. So constant time extended to speculative execution. Okay, so we do have a way of expressing contracts. So the key point now is, what can we use contracts for with compilers? Well, the key in our approach is making the compiler contract aware. So the point is that the compiler is going to be parametric in a set of contracts, where each contract effectively defines a different target language for the compiler. So all the contracts target the same syntax, but they will have different trace semantics that result from the details of the contract, and let's say the leakage model. So now we can lift the existing secure compilation criteria to contract-aware compilers. And we simply say that a contract-aware compiler is secure if it is secure for all the contracts that are supported. Okay, so if you consider a property like constant time, now we can have different contracts, such as those that I've shown you before, and we can prove that the contract-aware compiler preserves constant time for the set of contracts, right? So depending on the underlying guarantees of the processor, we will know that the compiler satisfies still preserve constant time. Okay, last slide. What I want to do here is try to put everything together by illustrating what it means to construct an end-to-end secure system using our contract-aware secure compilation approach, or CASCO for short. And as an example, I'm going to focus on constant time. Okay, so there are 3 steps. First, the programmer needs to ensure that the source program in constant time is constant time in the source language. Okay, that's the thing that the programmer should focus on. The next step, well, we have a Casco compiler that ensures that constant time is preserved for all contracts under consideration, where each contract, as I said before, captures a slightly different leakage model, such as, CPUs with and without speculative execution. So the key point here is that the secure compilation proof only has to go up to the contract level. There is no need to actually play with details of the underlying hardware semantics. And the final step is that, well, hardware engineers will provide contracts that each of the processors that we want to run our system on will satisfy, ideally together with proofs. And the key point is that by combining all these 3 proofs, so source program is constant time, compiler is preserves constant time for all the contracts, and a specific hardware satisfies the contract, then we can derive that running the program on the underlying hardware still preserves constant time. Okay, so running the program on the hardware runs in constant time. So the key point is that Casco allows you to split the security proof for an end-to-end system in different blocks, right? And across different actors, so that, at least my opinion, all these proofs are simpler than having to carry out the entire proofs end-to-end. Okay, I think that's it. So as I said before at the beginning, this is a very long-term project. We don't have many results yet, so we just started exploring it, both at the hardware and compiler levels. We do have an extended abstract with a few pointers and a few more details on the idea, and I'm happy to have a chat about this project and any questions you might have.